great pleasure to have Tiago Mendes Santos here, who's going to speak about many-body physics through the lens of machine learning. So we have access to you, so we're translating by YouTube, but I'm not sure if we're going to be able to read the questions by chat. We don't have a signal here. But in any case, hopefully by the end of the seminar, we'll get something.
All right. Yeah. Okay. Yeah, it's a pleasure to be here, and thanks for the invitation, Nathan. Yeah, today I want to talk about some works that I've been doing recently. So basically, I did these works that I will talk here. I did in 3 different places, like first in ICTP, in Trieste, and then Max Planck, and then University of Augsburg. So where's the place that I'm now doing a postdoc? So yeah, the main topic is like trying to use like some concepts and techniques of machine learning in the context of many-body physics. Okay? That is the, let's say, my main field of research. Okay, so here just to mention some examples of many-body systems, right? So we have materials, right? The high TC cuprates. We also have like what it's called quantum simulators and also superconducting supercomputers, quantum computers, right? So many-body systems are everywhere, like. And the idea is that we want to study, so the main feature of this system is that to have an ensemble of particles that interact very strongly, right? So, and the idea of my work is basically, so just to summarize, is to study microscope lattice models that describe the physics of these systems, right? So usually you are interested in access thermodynamic properties, dynamics of these models, and so on. And the physics that I am interested in is summarized here, right? So usually I'm interested in understand what's the many-body phase that appears due to these interactions, and also quantum phase transitions, and also correlations in the system that are like of quantum nature, right? So that it's like entanglement, for example, okay? So the idea is that one aspect of my work is that typically to study this kind of system is super hard, right? So you have to deal with these interactions somehow, right? You have to solve the Schrödinger equation for a many-body system. And typically what I do in my work is that I use computational tools to solve, to access properties of these models, right? So here I mentioned some of them, like exact diagonalization. So the tool that I use more is it's called quantum Monte Carlo technique. And also more recently, I'm also using what is called this new method that is called neural quantum states that I plan to talk a bit in my talk about this. Okay. All right, so now let me try to give you an idea of a specific system that I'm interested in, okay? A specific many-body system that I'm interested in. And the systems are called synthetic quantum systems. Okay, so the idea is that nowadays it's possible to realize in the lab quantum many-body system in a controlled way. Okay, so here I mention one example: this Rydberg atoms in optical tweezers. Okay, so the idea is that in each side here I have an atom, right, that is trapped by an optical tweezer, and these atoms can be in 2 states, like in the ground state or in what is called Rydberg state, okay, that is a highly excited state. And the idea is that when I highly excited the atom in this Rydberg state, the interaction between the atoms can be super strong due to this, basically it's a van der Waals interaction, right, due to the dipole moment of the atoms. And to summarize, like the physics of these systems, of course, it's much more complicated than that, but the idea is that we can, with this system, we can realize this kind of Hamiltonian, right? That is called Ising-like Hamiltonians, okay? So basically, we have an interaction term, a transverse field, and an on-site energy term. But you can do this in a controllable way, okay? So basically, this is the kind of Hamiltonian, that's just one example that I'm interested to study in my model, in my research. And then, yeah, so here I'm being very generic, but in principle, you can realize 2-dimensional systems with this, let's say, with this approach, this experimental approach. Okay? So you can shape the lattice with these optical tweezers. Okay? So you can realize 2D system with different geometries, like triangular lattice, like honeycomb lattice. Okay? So here is like, so here is the transverse field, okay, that is like the field that excites the like the atom, like from the ground state to the Rydberg state, okay? And this term here is an on-site term, it's like a longitudinal field, okay?
What is delta?
So delta, yeah, delta is related to this longitudinal field, right? So basically, delta controls the shift here, okay, of this highly excited state.
Okay, say what the relation of this Hamiltonian system is. I just can't follow. Well, what is the sum of the MI? Why is that? I just don't understand. The first term I understand. I don't understand the second.
Yeah, so basically, yeah, so the second term is this transverse field, is the field that excites the atom from the ground state to what is called Rydberg state, right? So it's this omega term here, okay, that I'm pointing here. And the last term is the delta, is a term that, with this term I can shift the resonance, this resonance here, okay?
So what is external and what is internal to the system?
Yeah, external, all these fields are external, you can control. Yeah. Yeah. Right. Okay. Yeah. Yeah, indeed, yeah. It's, I think here the idea is that I won't focus on a specific Hamiltonian, but I wanted to give this example. Okay, but the idea is that with this system, you can realize the many-body phases that is described by this Hamiltonian, okay, in a tunable way. All right. So you can realize like quantum many-body phases and also coherent dynamics. Okay. And also you can measure. So another aspect of this experience that is interesting, you can prepare a quantum state, but you also can access properties of this state, like for example, local properties, right? So here's a 2D lattice, okay? And this is like a fluorescence image, okay? So these bright points here represent like sites that are like excited in this Rydberg state, okay? So then you can really measure like what's called wave function snapshots. Okay? You really can do like a projective measurement in this quantum state. Okay? So this is the second, I think, important aspect. And then like usually like one thing that people are interested in, and also I'm interested in my work, is to study like quantum correlations in this system, like entanglement. Okay, so entanglement, the idea is that, so basically when your system is described by a wave function that cannot be written as a product, right, of part A and part B, right? The idea is that there are a lot of interesting things that happens when you have this condition, right? Basically, the system is entangled. So then you have like correlations here, like this from quantum nature, like non-local correlations. And so entanglement is usually something that I'm interested to look in my work. Okay? But here I won't focus in this aspect. I just wanted to mention that, right? So what I want to do in my talk is more related to like applications of machine learning techniques to study this kind of systems, right? This kind of Hamiltonian. And here, so basically here is the outline of my talk, okay? So basically I will talk about 3 topics, okay, that are like summarized by these pictures here. Okay, and the basic idea is that at the end I want to use like these machine learning concepts and techniques to study like questions related to many-body physics, right? And these are like, let's say, the main 2 questions that I'm interested in, right? The first one is how to characterize many-body states, right, using these new concepts. And the second one is really related to how to solve a many-body problem, right? How to, let's say, compute the ground state of a many-body model, right? Of a system that, a model that describes a system that is strongly correlated. Okay, so this is the 3 topics that I will try to cover here, right? And first I will focus in this part here. Okay, so here is really about physical data sets. Okay, so basically we have a physical data set that I will explain to you what is, and then how to extract physical properties of these physical data sets, right? And here, the 2 things that I'll talk about, the first thing is it's called intrinsic dimension. That is a property of data set. And the second thing that I will briefly mention, this is still an ongoing work, what we call it wave function networks, okay? So then I think the point that when you talk about machine learning, I think the first thing that you need to have in mind is that we have a data set, right? So basically, for example, here I have a bunch of images, right? In these images, I can represent, right? So each image here can be represented as a line here in this file, right? Where 0 is black and 1 is white, for example. Okay, so then this is a data set. And then with that, I can use, for example, neural networks to do image classification, right? So then I draw in my tablet 8, and then I can recognize that this is indeed 8, and so on. So this is just an example. But what I want to stress here is that we need a data set, right? And in physics, we have data sets, especially in many-body physics, we have data sets everywhere. Okay? So let me show two examples of, let's say, physical data sets. Yeah, we'll talk both simulations and experimental. Okay? So now, first I will give, let's say, simulation data set that I get in simulations, and then a data set that I can get in experiments. So here, the first example, I think, is the simplest one, right? So imagine that you have a system in equilibrium, right, at the temperature beta, right? And then you have your partition function, right? So the idea is that this partition function, in principle, is a sum of exponentially large number of configurations, right? But most of this configuration has a weight that is 0, right? Essentially 0, right? And what I can do is that I can do an importance sampling of this partition function, right? I can use a Monte Carlo method to select the, let's say, the states that has higher weights. And then you have a bunch of Ising configurations, for example, right? And this is my data set. Okay, so each image here, you'll be, again, aligned in this file, right? All right, so this is an example of data sets that I compute, let's say, that I get in a simulation, right, in a Monte Carlo simulation. Of course, I can also consider quantum system, right, in principle here, and then consider quantum Monte Carlo, okay? But the idea is that, right? So an example of, let's say, experimental data set is what you call wave function, snapshot, right? And it's related to these experiments that I mentioned in the beginning, right? And this possibility that they have of measuring, doing projective measurements in many body states, right? I won't enter in the details how it's done, this measure specifically, but the theoretical idea is that I have a wave function, right? So that is a sum of, in principle, exponentially large number of configurations, right? So D here can be, for example, 2 to the power of n, right? Where n is the number of sites, right? But what I do, when you have this quantum state, what you do, you can do like projective measurements, right? Then when you do this, the wave function will collapse to a certain state, right? And if I do that a certain number of times, what I'm doing is I'm sampling my wave function, right? And then at the end, I have a collection of wave function snapshots, right? This is an example of data set as well. And this can be, let's say, measured in these experiments with Rydberg atoms, this two-dimensional arrays of Rydberg atoms, right? So then the question, like let's say the general question that one can ask is like if you can extract physical information from these data sets, right?
If you have the wave function, you have all the information you might dream of that system. What you want to do in orbit, you already have the wave function measured.
No, but you always have to measure something, right? You always have.
But you show
yeah.
that you want the wave function. What else is required?
So you have to choose something to measure, right? Like correlations, for example, to characterize your system, right? Let's suppose that you want to characterize, let's say, an antiferromagnetic, right? You have to choose another parameter, for example, right?
What is the wave function good for? That is the wave function of the system, right? Psi.
Yeah.
So I have all the information I need for the type of the system. And what the correlation function, everything.
But if it's a many-body wave function, you have somehow to extract this information, right? So this is not. Yeah, but my point is that we have to. You have to choose something to measure, right? Like correlations. Like I agree with you that if you have your quantum state, you can. Yeah, but this is not a trivial task, right, in principle. Right?
No, my son asked me.
Okay, yeah, so this is exactly, I think, the question that I put here, right? Is the question that you are asking me, right? In a sense, right? Which physical quantity to measure, you have to measure, right? To characterize my wave function, right? And this can be a tricky question, right? So if you have a topological transition, for example, a topological phase of matter, right? That you cannot characterize by local correlations, right? So this is an example that is not a trivial task, right? But indeed, what we are doing here is that we are supposing that you have our wave function and you have somehow these data sets, okay? But what I'm claiming is that this is like extract information for a quantum many-body wave function is not a trivial task, right? So another point that I won't answer this question, but also something that I'm thinking about is that if these like new tools that I will show now can also be used to characterize the complexity of many-body states, right? Or like answer this question, how difficult it is to simulate a many-body system in a classical computer, right? Okay, indeed, so these questions were raised like 5-6 years ago, right? 5 years ago, in this paper here, right? And the idea of this paper is to use what is called a neural network, right? In a supervised way. So basically, you have like here again. I use the 2D Ising model as an example. So you have your 2D Ising model. And then you can train your neural network to characterize a configuration, right? So if it's Faro, if you feed here a configuration that is Faro, then it gives Faro. If it's disorder, it gives disorder, right? So you can characterize the phase of your system this way, right? So this is a simple example, right? Of course, this was also applied for more exotic phases, like topological phases that you don't have a local order parameter. Another example, this is more related to the things that I will do here now, is related to what is called unsupervised learning, right? And the idea of this method is to somehow learn about the physics based on properties of the data set. And what, in this example, in this paper, what was done was to use a technique that is called dimension reduction. More specifically, it's called principal component analysis. And the idea of this technique is to project this data set. So basically, this data set you can think as like points living in a space of high dimension, right? Where the dimension is the number of spins, right? And this technique, it projects in a simple way, actually, in a 2D plan, right? So here, these points are like configurations for different temperatures. So here's high temperature, so here's close to the critical point, and here's in the order phase, okay? And the idea is that in the order phase, you can see some structure in your data set. More specifically here, you see two clusters forming, right? And these two clusters are related to the order parameter of the 2D Ising model, right? That has a symmetry that it's Z2 symmetry, okay? Yeah, so you can compute, for example, the first principal component here that is not shown, and then you plot as a function of temperature, and then you see that, so basically it's the size here of the XX here, and then you show that this quantity has a behavior that is similar to the magnetization, okay? But from these pictures, you cannot see the transition. All right, so but this is, again, it's not our work, but what we try to do is try to learn something about data sets without any dimension, any kind of dimensional reduction, right? Since really look the data set as a whole, right? And what we did in these works here, these two works, was to analyze a property of the data set that is called intrinsic dimension, okay? So now you enter more in my work. And then let me try to explain what is this intrinsic dimension mean, right? Okay, so basically so first with a simple like description of this quantity. So basically in a few words, like in a roughly way, this quantity is is a number that describes the minimum number of variables that you need to describe the important features of a data set, right? So here in this example, I have a data set with 3 coordinates, right? But the idea is that I can describe this data set with a single parameter, right? So basically, despite this data set is embedded in a space of 3 dimensions, the effective dimension or the intrinsic dimension of this data set is equal to 1, right? So this is the intuition behind this quantity, right? So here now is a physical data set, okay? So here basically what I did was I simulated this simple model here. So this is an XY model, classical XY model, with just 3 spins, right? And here I plot the data sets that are generated by this, the coordinates here of these angles, right? These 3 angles here, θ1, θ2, and θ3, right? And the idea is that if I look in configuration space, like for low temperature, very low temperature, my intrinsic dimension is 1, right? So basically, my data set is, I just need 1 parameter to describe my data set, right? The system. But for a very high temperature, my intrinsic dimension is equal to the number of coordinates of or the number of spins of my system. Right, so here it's a very simple example, but already showing the intuition behind this quantity. Right? Okay, the question is how to estimate this intrinsic dimension. Right? And then what you do later, you try to show results of this quantity across phase transitions, right? Classical and quantum phase transitions.
In that example, the chain was open, right?
Sorry?
It was an open chain in the example you got.
Was an open chain, yeah. No, but yeah, it's an open chain. But it doesn't change the result here. Because okay. So in principle, so here, of course, I would have to consider periodic bounding conditions. So I would also have points here, right, if you want. I just not show this.
Suppose t instead of being 0 was 0.5, very small.
Yeah.
You still say it's one-dimensional, or you say
It depends on the scale that you measure, the intrinsic dimension.
how do you define that scale?
Yeah, so I will show a way to do this, right? So the method that we use, indeed, we can define a scale, like, okay? And I briefly mentioned that. I will mention that now that you asked that. It's crucial, yeah. You're right. So indeed, yeah. Yeah.
Is it true that it's crucial that it's open? If it was closed, it will not be this picture, right?
Yeah, I think here, I mean, the precise picture maybe would be a circle, right? Because this angle, you have periodic bounding condition, right? So indeed, but it would be intrinsic dimension equal to 1 anyway, right?
I don't know, that's my question, because you like frustration.
So there is no frustration here because it's a ferromagnetic state, right? So for that reason, consider periodic or open bounding condition doesn't change. If it was an anti-ferromagnetic, I agree with you, but here you have this J is positive, right?
So what would happen if J is negative? What would be
Yeah, for sure, I think the intrinsic dimension will still be 1, right? But I think this picture would change. Actually, I have to think about this more specifically. Yeah, I have to think about. Okay, I didn't. Yeah. Yeah. All right. So, yeah. Now I try to describe how to, let's say, to estimate this quantity, right? And indeed, it's I would say it's still an open problem. This how to access this quantity, and there are different methods to do this. So here we use what's called a geometric approach, okay? That's in a sense is similar to what is done to measure like fractal dimensions in the context of statistical physics, right? So more specifically, the method that you use is called a nearest neighbor based estimator, right? And the basic idea is that the intrinsic dimension is related to the statistics of nearest neighbor distance, right, in configuration space. So here again, I'm showing this synthetic data set just to illustrate that. So the idea is that for each point in your data set, right, you can compute distance, right? So here you just use Euclidean distance, right? So R1 and R2 as this two nearest neighbor distance of each point, you can compute this distance. Right? And you can relate that with the intrinsic dimension. The basic intuition of this relation is given by this formula here, right? So again, it's a purely geometrical approach, like at least the intuition behind. So if you draw here a ball around a point I, right, with radius R1, and that is the distance between I and the first nearest neighbor of I, and then draw another ball around another hypersphere, let's say, around I that is related to the distance between the I and the second nearest neighbor to it, right? Basically, the volume of this shell, right, the hypershell, is related to the intrinsic dimension, right? And what was shown in this paper is that the probability distribution of the relation of the R2 and R1, right? R1 is the first nearest neighbor, R2 is the second nearest neighbor, is related to the intrinsic dimension. Okay, so this is the basic here. So this is the formula that we use to compute this intrinsic dimension. Okay. Again, one important aspect, this is a local measure. Let me show in this graph, yeah. And then what you can do numerically is that you can compute empirically this probability distribution, and then you can fit this formula, right? So what I show here in this graph is not f, but is the cumulative distribution of function. It's just more convenient to do the fit with the cumulative distribution function. That is just the integral of this formula.
So just to understand, is this the definition of intrinsic dimension, or is this a consequence of definition? I just don't know what the definition is yet.
Yeah, actually, I would say that for this, how can I say? So there actually, I didn't say, but there are certain assumptions that you have to do to write this formula, right? So one of the assumptions is that these points, this data set, were generated by a Poisson process, right? So basically, the density between these 2 points should be constant, locally constant. Okay? So but this is not, so let's say I think there is no definition, like a closed definition for the intrinsic dimension, right?
I understand intrinsic dimension 1 or 2, but what is intrinsic dimension 1.5? How do I distinguish 1 from 1.5?
Yeah, I think there is it's like the fractal dimension, right? It's like.
I don't know, but I'm sure it's defined fractal.
Yeah. Yeah. So this is an approach to compute the intrinsic dimension, let's say, but there are other approaches. So if you use another approach, the formula will be different. So for this. So this formula, yeah. So basically, I won't show the deduction of the formula, but the basic assumption is so the starting point is this one, right? So and then you have to do certain assumptions, and then you can show that can I explain like this? Yeah, so yeah. Yeah, I cannot, like, in a few words, I cannot explain like in details how to arrive at this formula. Okay? But the basic assumption is that, so you need to assume that your density is constant within this distance between R1 and R2. Yeah. So, yeah, well, I'm trying to explain in a way that it's not so mathematical. Yeah, what you show is that, okay, now I remember. So what you show is that at some point you show that the probability distribution associated to the relation of this VI and VI1 is an exponential probability distribution, right? So, but it's a mathematical formula. I have to, actually, I don't remember all the details how to arrive there. That. Okay, so yeah, but what we do is that we generate this data set numerically or also experimentally use experimental data set, and then you can fit this formula say empirically, and then you can compute this intrinsic dimension. And in this case, we get what we expect, right? 1 or 3, right? But there are two important aspects about this calculation. The first one is this is a local feature of the configuration space. Okay, so the idea is that the intrinsic dimension can change. So I can have a data set that has an intrinsic dimension that's one number in one, let's say, region of the data set and another number in another region. And another important aspect that this intrinsic dimension is a scale-dependent quantity, right? And one thing that can change the scale is the number of points in the data set, right? So basically, the number of points in the data set. So here, I think there is this example here. I think this picture already illustrates that, right? So if you zoom in here, okay, you can see that the number of directions that I have to use to describe my data set is not equal to 1, right? So, and what changed this, let's say, this scale is the number of points in your data set. Okay. Okay, I don't know if it's clear that. So basically, the number of points in the data set change the average distance between this quantity. But in this large scale, the intrinsic dimension is equal to 1. Right? So basically, in our calculations, you always fix the number of points in the data set to a certain value. It is an important thing.
Do you have a less trivial example where to show us? Because these two examples are too simple. Is it possible to see this dimension changing between some value and another value, something a little bit less trivial?
There are like for synthetic data sets, right? For physical, I didn't find anyone yet. It would be nice to. I mean, now I will show like the intrinsic dimension of data sets that has a huge dimension, right? The total dimension is not equal. The embedded dimension, let's say, is not equal to 3, but it's like. So for a simple example that you can visualize, I cannot think about another example apart from this one, right? This is less trivial. So the examples that I will show now, I cannot visualize anymore, right? Like here. Okay. And this is what we did here, right? So basically, so now the idea is that we can use this approach, right, to compute the intrinsic dimension of these physical data sets that I showed before, right? That has a huge dimension, right? Huge means like the number of sides of the lattice. And the idea is that to generate data sets for different values of temperature, right? And then you can compute the intrinsic dimension as a function of temperature, right? And then you did this for like classical systems. You study different kinds of phase transitions, like second order, first order, also like topological phase transition, Belezinska-Selitaulis. And the idea is that you always fix this number of points, right? That is related to this scale that I measure in the intrinsic dimension. So here now it's come more physics, right? So basically now.
Can you go back one slide? So there's a lot we know about physics of phase transitions, first order, second order, constant Taubes transitions, etc. What exactly are we asking? What is the physical question we are trying to solve? Or what physical question will you solve?
Yeah. So one I think is, let's say, trying to find new ways to detect phase transition, right? So I think the Belezinska-Selitaulis is an example. We know how to characterize this phase transition very well, but we know that we cannot characterize with local order parameters, right? So here we use examples that we know everything about the physics, right? But the idea is that this is more like a, let's say, benchmark for our approach. But the goal is that, like, suppose that someone gives you a data set, let's say an experimental data set, that you don't have so much information about the physics, the Hamiltonian, for example. This can happen. And then, in principle, you can analyze the physics of the problem just analyzing properties of the data set, right? You don't need to say, okay, I want to calculate another parameter, like a magnetization or a kind of correlation function. So this would be one motivation, right?
So the idea is when ID is 1, you have an ordered system. If ID large, you don't have an ordered system.
The intuition is that, but you see that for this,
So I
yeah,
But for other systems, I
yeah.
this connection with ID and location of a system.
So this we didn't know as well. So this work was, so now I will show the results. And then actually, when you start to work with this, we thought that the ID would be maximum close to the transition, right? Because it's like if you use this idea that the ID is measuring like the number of degrees that you have to describe your system, but it's the opposite, right? So let me show the results now. Okay, so here, some example of results. So here I'm really looking at the intrinsic dimension of a huge lattice, like let's say huge data sets, right? So basically each data set is embedded in a dimension that is equal to L squared, right? So here's a square lattice. So I think your intuition is right. So basically for high temperature, the idea is it should scale with the number of sides. But then if you decrease the temperature, if you enter in the order phase, it goes towards 1, right? But in the middle, we found this funny behavior here. The idea has a minimum, okay? And the other interesting thing is that this minimum, if you change the system size, shifts towards the critical point, right? So we could even could really do kind of data collapse, right? As we do for physical observables, right? So when you want to characterize phase transition, we do this finite size scaling, right? And then we can compute critical exponents, right? So let me show another result for the 2D XY model, right? So here's a different, so we still have a phase transition here, but the nature of the transition is completely different.
So this number, do they agree with the system that you know how to solve this exactly?
Yeah, yeah. I mean, with error bars, right? So the 2D IC model, these results are no exactly, actually, right?
This agrees with your
Yeah,
computation of this.
exactly, yeah. Thanks to us, yeah, I forgot to say.
Sorry, so you must have a definition of ID, right? What's your definition?
Yeah, the definition is for this method. So what I'm saying is that there are other approaches to compute the ID, right?
Your definition.
Yeah, so here my definition is exactly that formula if you want, okay? And the meaning, at least like qualitatively, would be like the number of directions that you have to describe, that you have to use to describe your data set locally, right? So I think this is. Okay. And here, let me, before comment more about this minimum, we also calculate that for another transition, right? This BKT transition, right? And you also can do, numerically, you can do this data collapse, right? As you do for physical quantities, right? And you also see, for larger system, you also see this minimum here, right? So, so one way to understand this minimum is try to connect the distance to this distance. Oh, sorry, try to connect this intrinsic dimension to this distance, right? To this statistics of distance. So here I don't have the formula, but we can show that the intrinsic dimension should scale as 1 over L as the ratio of two distances, R2 and R1. Okay. So basically, so this we show numerically, empirically, that this distance is related to the correlation length, right? So then for that reason, you can understand why you have the minimum. Okay? But you still don't have a qualitatively picture why you should have a minimum of the intrinsic dimension across the transition, close the transition, right? Okay. This one? Yeah, so here I'm just, so it's the same points as this graph, right? But I'm just rescaling things, okay? And this rescaling of things is motivated by the way that the correlation length diverge close to this transition. So here you really use an input, right? So I'm really, let's say, for that reason, I had to choose something that I know, right, to benchmark the approach. So I'm just rescaling these numbers here.
What do I learn from this graph?
Sorry?
What do I learn about ID from this graph?
So yeah, what you learn is that so this ID can be rewritten as a universal function, right? So because you can rescale the ID for different system size and for different temperature in a same curve, right?
So the ID scales like L to the zeta.
Yeah.
That's what you're saying.
Yeah.
That just doesn't know the scale.
Mm-hmm. So we are really using this finite size scaling hypothesis, right? So basically, your physical quantities is like close to the critical point, right? It's determined by this length here, right? Mm. Okay, I think, yeah. So you also explore that for quantum phase transitions, but here it'll be a bit faster. And the idea is that we can also define quantum data sets, right? So as I'm running out of time, I will be a bit more fast in this part. Okay, but the idea is that you can also compute this intrinsic dimension for quantum phase transition, right? Quantizing model, and we also observe like qualitatively the same results. You have this minimum close to the critical point, right?
You are not going to explain the physics of this question, I just want to show it.
You mean the phase transitions?
Why do they scale like some power of L? Why do they collapse, etc.? You are not going to.
Yeah, so here so here, for example, is also related to here again you have to use this as an input. It's also related to the scaling of the correlation length, right? So this is the same transition that I showed before, like this BKT transition. And so like critical features of physical quantities for a finite systems, right, is expected to scale like 1 over L squared, like, but due to that, right, because at the end the correlation length, in this case is not T, right, because it's a transition at temperature equal to 0, right? And yeah, so this. And here it's a second order transition, right? It's a quantizing model. And here the position of the minimum is supposed to scale as 1 over L. Here also there is a critical exponent, should have a critical exponent. But the critical exponent here is equal to 1, right? It's the critical exponent associated to the correlation length. Right? Okay, I wanted to move to another, now I think I spent a lot of time in this, but it's fine. Yeah, I think that the main message of these works was that, right, that universal critical behavior of critical points can be learned through generic properties of data set, right?
I did not get this message at all. It's just like last two slides. Can you please go through one of these slides at a more reasonable pace? It's impossible to get this last slide. Can you maybe show the first one?
Yeah.
Sorry, I just want to understand, because everything was very simple and then suddenly it was super fast. So here, for example, I get there is a minimum at some value 10 times L to some power, for example, right? In your middle plot.
Yeah.
Why do I expect the minimum there? Why is power L?
Yeah, so here, yeah, sorry, I should maybe explain finite size, more about finite size scaling, right? So here I'm really already using the finite size scaling hypothesis, right? So basically, physical quantities, right, due to the divergence of the correlation length, right, should, I don't have the formula here, but for a finite system, L should be equal to L times to the power of an exponent, right, the critical exponent, times a universal function, right? So this is, you can show that with a normalization group, right, techniques, okay? And here I'm really using this finite size scaling hypothesis, right? Exactly. Yeah, but this also happens with physical quantities, right? You should always, when you do numerics for a finite system, you should always try to compute empirically, right? These critical exponents. Is always, I mean, you should know that, so that the finite size scaling hypothesis holds, right? So that a physical quantity f should, with the exponent you don't know, but it's exactly what we can calculate here, right? By fitting, exactly, calculate. Yeah, I think the non-trivial aspect of this result is that we show that the ID has this scaling behavior, right? Yeah, so we also did that for other examples of second-order transition that has different critical exponents. And then you play the same game, right? You do this, let's say, empirically, and then you compute a number, right, from these methods, right? And then the number that you get is in agreement with the universality class of the other model, right? So we can really access this quantity. So I think the message is, in my opinion, the main message of these works is that, right? This quantity, X-bit scaling behavior, right, across critical points. But you should use finite size scaling hypothesis, right? Indeed, for the other transition that I show, the formula should be different, right, of the finite size scaling hypothesis, because I'm talking about BKT transition, right? Okay.
Do you have an understanding of this ID in the continuum?
Which case specifically?
In any of these models. At the critical point, what is the definition of this ID in the continuum field theory?
In a continuum field theory. Yeah, I should think how to define a data set in a continuum field theory, right? Because you should discretize somehow, right?
So let me maybe then ask. So is this quantity easier to measure than other physical quantities? That's why you like it? Why should we use it? Because this quantity you are not giving us a very physical definition of what's the physical significance of this curve, right? You are just showing this curve collapse, fine. But all physical quantities will, right? I mean, in any specific heat will. Is this easier to measure than the specific heat or something?
In certain cases, yes, right? For the BKT transition, right? So usually you need to compute transport properties to characterize the transition. That is difficult to measure. And here I would say that it's easier to compute this quantity. But I think it's really related to the meaning of this quantity, right? So in the beginning I try to, like with simple examples, right, which are the examples that I can give intuition, I try to convey that this quantity is related to the number of degrees of freedom that you have to use to describe your system, right? So I think that this conceptually is also important, right? The fact that we have a minimum of the ID or a local minimum of the ID in the vicinity of phase transitions.
Okay. Why is that a minimum?
So you don't have yet a clear understanding of that, right? A conceptual understanding of that, right? So you can relate, as I said,
the most important feature of all, right? Is the fact that it's a minimum.
Yeah.
And you are saying that because it's a minimum, we should use this as a real tool. But then you should understand why, right?
Yeah, so this is something, yeah. In fact, we have an idea of the scaling. Why should the scaling of the ID should be a minimum? And it's the thing that I was mentioned, right? That the ID at the end is related to the ratios of distance in configuration space, right? I think the formula is not here. I put in the supplemental material of the presentation. And we also show, so here is just part of the story, but you also show that the distance in configuration space can also be used to characterize the transition, right? So we show that the distance in configuration space is also related to somehow with the correlation length. So and then we can connect this intrinsic dimension to this. So we also use another method to compute the intrinsic dimension. You show that has a minimum. If later I can show this. Right. So yeah. So here I think I show too many examples, right? But the idea is that this quantity X bit universal scaling behave. Right. Okay, so as I'm running out of time, I think I will skip this part, right? So the second part would be to try to have a better understanding of the representation of these data sets, right? So far, I just talk about the feature of this data set. but you are also trying to connect these, trying to understand better this representation of data sets, but without doing any kind of dimensional reduction, right? And one thing that we are trying to do is trying to connect, connect this view of the system, right, in terms of data sets with the physics of graphs, right, of complex network, right? So it's really try to represent your data set as a graph, right, high dimensional space, right? Okay, I think, yeah, okay, let me talk about this and then I skip the last part. And so the idea is that, yeah, graph you have like, simplified way, you have points, right, and then you have these links between the points, right? But then for like complex networks, the structure of this graph can be super complicated, right? And the basic idea is that we can represent, like in a simple way, that I will discuss now, physical data sets, right, of physical configurations. So the idea is that physical configurations are points, right? So here my wave function snapshots are points in a high dimensional space, right? And with this idea of defining distance between the points that I mentioned before, you can define these links between the points, right? So basically, this is the definition of distance between points, the same one that I use to compute the intrinsic dimension, right? And then the method, the idea is to define links, right? So basically, the idea is based on this prescription here, right? So if you have like 2 points, right, it is within a cutoff distance that I have to define a priori, I put links between these points, right? If these two points that I'm looking, it's the distance between them is larger than this cutoff, and then they are not linked. Okay, so then I can define these graphs, right, in this way. So basically, this is with this basic prescription, we can define this, what we call wave function network, right? So this is a way to represent the data set, right? Okay, and this is something that has been studied in different contexts, right? In the context of complex networks, and there are different questions that you can raise when you have a complex network, you have a graph, right? A very complicated graph. But one of these questions is related to this quantity here, that is called degree distribution, right? So basically, this quantity tells us the number of connections of each point, okay? So basically, here there are 2 examples of graphs. So the first one is like a random graph. Right? So in this case, the probability distribution, the degree distribution, is a Poisson distribution, right? There is nothing special. But the interesting thing is there are a certain kind of complex networks that we observe, like the internet, for example, that has that can have like a power law distribution. Okay, so this is called a scale-free network. And so you also explore this idea, and what we show is that so here we compute this degree distribution, right? For a data set that is defined like very far from the transition, and then you show that it's really a Poisson distribution. And the interesting thing that you notice is that close to the transition, right, this distribution has this long tail here, right? And it's well described by a power law distribution, right? So this is an indication that we can have this wave function network and feature a scale-free structure, right, in this. So this is more a conceptual result. So here, we are trying to explore more this direction, right? If you like this field of complex network and tells us more about many-body physics. So here is just it's a first result, right, in this direction. Okay, and then the third part. So here you just mentioned the motivation, right? So the problems that I discussed before is more related to analyzing data sets, right? Physical data sets, and try to extract somehow physics from this physical data set. But here I'm also employing like also techniques for machine learning to solve the many-body problem, right? like to really solve the Schrödinger equation for the models that I mentioned in the beginning. Right? And more specifically, I'm interested in studying dynamics, quantum dynamics. And there are like different questions that is being raised in the context of quantum dynamics, like for example, how a closed system reach thermal equilibrium, right? And if, or when it fails, right? And also questions more related to, let's say, to materials, like to compute, to simulate observables that can be measured experimentally, like dynamical response functions and so on. And the basic idea is that, okay, so why it's so difficult to solve the many-body problem, right? So basically you can say that the wave function, so the number of terms that I have to consider to describe my wave function is exponentially large, right? And then one idea that was proposed recently, like 5 years ago as well, was to try to use what is called a neural networks to represent wave functions, right? And the basic idea is that you can use like physical principles, like the variational principle, to train this neural network, as is done like in other contexts, like in image recognition and so on. And I'm also interested in analyzing different aspects about this method, right? So I think this method is still under development, and so I'm also working in these different aspects related to this method. Right? And so here is just an example of results. So I'm trying to compute what is called dynamical response functions, like ring functions of many-body systems using these methods, generalize these methods to compute this quantity. And I think here's just one example of results. Okay, with that, I summarize my talk, right? So I tried to convey like different directions that I've been working with. So some of this work is still going on, right? Especially the point 2, the point 3 is in preparation. But yeah, the first part, I tried to show this concept of intrinsic dimension, right? And I think the key point is that, my opinion is that this intrinsic dimension can reveal universal properties of associated to critical points, right? In the second part, I also try to connect, try to define what I call it wave functions networks. And in the third part, I discuss this new approach to solve, briefly discuss this new approach to discuss a new method to compute, to solve the many-body problem, right? Okay, there are also different directions that I'm also trying to pursue that is somehow related to these points to these conclusions that I mentioned before. Right, so one more technical question is related to let's call it sign problem in quantum Monte Carlo simulations. So trying to use this quantity, like the intrinsic dimension, to characterize physics when you have this sign problem. I think here would be really an example of situation that is intrinsic dimension. It's important, like in the sense that you cannot do otherwise, right? You cannot extract the physics with physical observables when you have sign problem. But the question is, what happens with this ID when I have sign problem? Also questions related to a normalization group. And also questions more related to applications of the method that I showed as neural quantum states for specific models, right, that are motivated by experiments. Okay. Okay, with that, I thank you. Yeah, so the question, it's still an open question, but the point is that we know that when you have the sign problem, if you want to measure a physical observable, you have to do exponentially large number of measures, right? Because basically the error of your measure is scaled as 1 over the average of the sign, right? I'm not so sure if this. But here we don't know yet, so in a simple terms is that we don't know yet how sign problems affects this quantity. Right? So the things that I'm doing, I really explore, like study situations that have some problem and compute these quantities. And so far, like the results that you get is that the sign problem affect less these quantities related to the intrinsic dimension. But the question that I'm trying to answer is that really that how the sign problem, when I have sign problem, affects this quantity, right? So let me try to, oops. Let's see if I have, Yeah, so basically, this intrinsic dimension at the end depends on distance, right? And so distance in configuration space depends on overlap of configurations, right? So when you compute a physical observable, you always, like, you have your configuration, and then you compute, let's say, the magnetization. Then, and here is different, right? Here it's and I'm trying to understand that, like when you have the same problem, how these quantities are affected, right, by the same problem. But it's, yeah, so the numerical results are very encouraging because it's really showing that we can, so it's less prone to problems when you have the same problem. But you have, it's still going on this direction of work.
And can you just put again, when you had the scaling of the fifth dimension was L to some power psi, what was psi?
Oh, yeah, so this is something that we don't know yet. And the problem is that, so the answer is, the short answer is I don't know. And the problem is that this depends on the, let's return. This number, right, you mentioned?
Yes, what was that psi?
Yeah, so we don't have a physical interpretation for that yet. Yeah.
But what does it come out to be? Is it 1 or 2 or 3 or is it?
So yeah, in the critical point, I don't have understanding of that. But if I'm here for high temperature regime, this should be 2, right? So the intrinsic dimension scales with the number of spins, right? And for the close to the in the order phase, deep in the order phase, this should be equal to 0, right? So the intrinsic dimension should be equal to 1. But close to the critical point, yeah, we don't have a clear understanding of what this mean, what these terms mean, like what this critical exponent mean.
But numerically, what psi do you get close to the critical point?
The value is something like 0.4, but we, yeah.
Yeah, this is a question from YouTube, from Carlison Miller. So he says, hi, in theoretical physics, we can have a problem when we try to include the chemical potential. Can you use machine learning to predict new phases that are hard to get in known methods?
Mm-hmm. Yeah, I think, yes, of course, depends on the context, right? So here I'm more in the context of statistical physics, studying models, right? And here I would say yes. So so there are different techniques, and here I'm showing like one example of approach. But for models, we can detect like phase transitions that you don't know, right? A priori, you can detect with this approach, for example. So this model is more like about phase transitions. Like this approach, what I'm discussing here is more related to critical phenomena. It's not related to phases of matter. But there are other approaches that you can use to learn like new phases, let's say, both in the context of model that know more, but I guess also in the context of materials, like people has been working on this direction. You can get your wave function just from the data, right? But so the method that I explained it is we need the Hamiltonian, right? Yeah. So here I was maybe too fast, but the nice thing about this method is that you are really solving the problem. Yeah. So basically here you don't have data a priori. You don't train with data. You train with variational principle. Like so basically it's like really minimization of the, yeah. But like if you have the data, you can also train your neural network to be a wave function. Yeah, so here is really like variational principle, like stochastic gradient descent. No, you don't change, yeah. But you can use this method for situations that the Hamiltonian depend on time. Or some parameter, yeah.
Sorry, can I ask, can you also tell us what is Xi for the Kosterlitz-Toulouse transition?
I don't remember, I have to go there again. The value. Pedro, I think, I have to check again, but I think it's also close to 0.4.
Okay.
But I can check in the paper.
Thank you.
I think both,
Isn't it more the idea that you get a sudden rather than a minimum out of this?
You mean a jump?
Yeah, because when you have order parameter, then you start from zero temperature,
Yeah.
order, so you will have.
Yeah, maybe I can show the results for first order phase transition that we also, I didn't include here. That is more like a sudden, like more a jump, as we expect for. Yeah, here we go. So here's the first order. So here the x here is super small, right? The range. If I put in a larger range, you would really see a jump, right? But so here's like a first order transition. So you have so the correlation length don't diverge, it's finite. But the correlation length here is not so small. It's like of order of 40, I think, Lattice parameter, between 30 and 40, if I remember correctly. So here's the 8-state spots model, right? So basically for a small system, you still see like a second order phase transition, right? Because your system don't see a finite correlation length. So you still see like a minimum here, right? But the scaling of this minimum is trivial. This is what we found. It's, so the exponent here is the dimension of the system. It's not like, but if you increase more the size of the system, then you have like a jump, I think, as your, yeah. Thanks, everyone. Yeah, exactly. Yeah. 102. Yeah, exactly. Thank you.
Você já desligou o microfone?
Não.